In 2020, two astronomers won the Nobel Prize for proving there's a supermassive black hole at the center of our galaxy. They tracked a star called S2 for 30 years, watching it whip around an invisible monster at 2.5% the speed of light. Case closed, textbooks updated, Nobel medals awarded. Now here's the problem. A paper published this week uses that exact same data to argue the opposite. That thing at the heart of our Milky Way, it might not be a black hole at all. It might be dark matter. And no, this isn't some fringe conspiracy. This is an international team of astrophysicists publishing in one of the most respected astronomy journals in the world. Monthly notices of the Royal Astronomical Society, the same journal where some of Einstein's contemporaries published their work. So let's talk about what they found, and more importantly, what it means if they're right. First, you need to understand what we thought we knew. Since the 1970s, astronomers have been watching the center of our galaxy. There's something there, something massive, something invisible. Stars orbit it like planets orbit the sun, except these stars move at thousands of kilometers per second. The star S2 comes within 120 astronomical units of this invisible thing. That's 3 times the distance from the sun to Pluto. And at its closest approach, S2 is moving at 7,700 kilometers per second. If you're keeping track, that's fast enough to cross the entire United States in about half a second. Whatever S2 is orbiting has 4.3 million times the mass of our sun, packed into a region smaller than Mercury's orbit. The only thing we knew of that could be that massive and that compact was a supermassive black hole, and that's what won the Nobel Prize. But here's where it gets interesting. A black hole has a singularity, an infinitely dense point where all the mass is concentrated. It has an event horizon, a point of no return where even light can't escape. These are the defining features. The new model proposes something different. What if all that mass is made of dark matter particles? Specifically, fermions, particles that obey the Pauli exclusion principle. They can't all occupy the same space, so they form a super-dense core instead of collapsing to a point. And this core would be so compact, so gravitationally intense, that it would bend light almost exactly like a black hole. Stars would orbit it the same way. The gravity would feel identical. Remember that famous image from 2022? The one from the Event Horizon Telescope? That glowing orange ring with a dark shadow in the center? Everyone said that's what a black hole looks like. Proof positive. Except a study in 2024 showed that a dark matter core, illuminated by surrounding gas, would cast an almost identical shadow. No event horizon required. Just extreme gravity bending light around an incredibly dense ball of invisible matter. So if both models look the same and make the same predictions, why does this matter? Because of what happens when you zoom out. Here's the problem with black holes at galactic centers. They sit there in the middle, doing their gravity thing. But the dark matter that fills the rest of the galaxy, that's treated as a completely separate thing, a halo surrounding the galaxy. Two different phenomena that just happen to coexist. The new model says they're the same substance. The ultra-dense core at the center and the diffuse halo spreading throughout the galaxy are both made of the same fermionic dark matter. One continuous structure from the heart of the galaxy to its outer edges. And here's why that matters. Recently, the Gaia Space Telescope mapped how fast stars orbit at different distances from the galactic center. What they found in the outer regions was surprising. The orbital speeds decline in a way that standard dark matter models didn't predict. But the fermionic dark matter model? It explains this naturally. The same model that explains the core also explains the halo. One model, 2 scales, everything connected. Now I need to be fair here. Most astronomers still think Sagittarius A star is a black hole, and they have good reasons. First, we've never actually detected dark matter particles. Despite decades of searching, they remain invisible in every experiment. Proposing that the center of our galaxy is made of particles we've never found is a big ask. Second, in 2018, the gravity instrument detected hot gas orbiting extremely close to the center. This gas was moving at 30% the speed of light. That's consistent with matter spiraling near an event horizon. A dark matter core might struggle to explain something that close, moving that fast. Third, and this is important, the new model isn't better than the black hole model. The paper admits the fits are essentially identical, They're not saying black holes are wrong. They're saying dark matter works just as well. For now. So how do we settle this? The answer might be photon rings. Black holes have a unique feature. Light can orbit them. Photons that come close enough can circle around multiple times before escaping or falling in. This creates distinctive rings in the light pattern around the black hole. Dark matter cores, no matter how dense, wouldn't have photon rings. There's no event horizon, no point where light gets trapped. The Next Generation Event Horizon Telescope and an instrument called Gravity Plus are both upgrading in 2026. They might have the resolution to detect photon rings. If they find them, the black hole wins. If they don't, the dark matter model becomes much more compelling. Think about what's at stake here. If Sagittarius A star is really a dark matter core, it changes how we think about every galaxy in the universe. Those supermassive black holes at the centers of galaxies, they might all be dark matter structures instead. The fundamental architecture of the cosmos might be different from what we assumed, and there's something poetically ironic about this. Einstein himself didn't believe black holes could exist. He published a paper in 1939 arguing they were impossible, too extreme, too weird. But the evidence seemed overwhelming, and eventually black holes became accepted physics. Now, almost a century later, we might be discovering he was right to be skeptical. Not because black holes can't exist, but because the specific object at the center of our galaxy might be something else entirely. The same data, the same observations, two completely different interpretations. In science, that's not a failure. That's exactly how progress works. You gather evidence, propose explanations, and test them against each other until one breaks. The stars are still orbiting, the shadow still glows, the gravity is still there. What changed is our understanding of what that gravity might actually be, and in a few years we might finally know for sure what's really lurking at the heart of our galaxy. Or we might find out we were asking the wrong question all along. Want more of the latest science discoveries that challenge everything we thought we knew? Subscribe. There's always another mystery waiting.